Hi, I'm Sage from UVM. Thanks for having me. I'm going to be talking today about a machine learning package I've been working on called the Brain Predictability toolbox. This package exists as a standalone version, which I'll show today, and we further plan to add a version to the deep. The overarching goal of the project is to provide a tool to help researchers more quickly and accurately use machine learning to probe large data sets like ABCD. Built in is support for a wide range of machine learning techniques, as well as baked in best practices surrounding cross-validation and the general machine learning workflow. In the rest of the time for this presentation, I'm going to take us through an example longitudinal machine learning question with ABCD data, predicting sex from only change in brain structure. The caveat here is that I'm going to try and get through the whole analysis in just a few minutes, but I'll do my best to step back at times to provide some higher level context. So in this example, we're going to be predicting sex, but as our input features, we're only going to allow the models access to the change in different structural measurements from baseline year one to the follow-up. We can specify this is by selecting as our event name the change from baseline year one to the follow-up, so baseline minus follow-up. So as I said, we'll be using sex as our target variable. We can go in and load and look at just that variable. And then what we can also do is go in and load sets of variables. So you can see I already have these predefined structural sets, but if we wanted to, we could go in and make new ones. If we come back here, we can see we have that default event name we set. We can also apply some basic outlier filtering based on standard deviation. You may also easily load and specify non-input variables and easily define subject inclusion or exclusion lists. In general, the GUI has been designed to try and be as user-friendly and as intuitive as possible. From data loading to each progressive project step, the idea is that the users walk through many of the key decisions that they have to make in setting up a proper machine learning experiment. Next, what we can look at is defining a reusable validation strategy. So it can be useful in machine learning to stratify by your target variable, which in our case is sex. So what we can do here is define stratify by sex as a reusable validation strategy. Here we're defining 20% of our data set or subjects to be reserved for testing subjects. We select stratify by sex as our validation strategy. And now we can see if we load the sex variable, the distribution of males to females is exactly preserved between the training and testing set. So that's the type of behavior. And then because we defined it as a validation strategy, we can also use it in different parts of the pipeline. So the reason we're defining train test splits at all is so that on the training set, we can compare different machine learning pipelines performance, which we'll define in the next step. And then on the test set, only evaluate whichever one works the best. On this page is the interface for defining machine learning pipelines, where a machine learning pipeline refers not to just a base algorithm like elastic net classification, but to any series of pre-processing or, say, feature selection steps applied prior to the base algorithm. The benefit to the pipeline is that all operations are applied correctly when nested in validation folds. So in this case, we define scaling on each input variable, and our base model is an elastic net. A key feature of the toolbox that we can see here is that we can select a predefined distribution of hyperparameters for different models. This helps take away some of the expertise needed for hyperparameter tuning. Note here that we can also specify a very specific hyperparameter search strategy using that stratification behavior that we defined earlier. So we're going to do the same thing, but for a support vector machine-based model. So again, this robust scalar. This time we're going to define a front-end feature selection method, which will also select a distribution of hyperparameters to optimize. That's just the percent features to keep. And then as the model, we'll do this SV, the support vector classification, and then again, select this predefined distribution of hyperparameters. And for our parameter search, basically optimizing those distributions of hyperparameters, we're going to do that random search, again, stratifying by sex. So for the last of the three pipelines that we'll consider, we're going to do a light gradient boosting model, or consider a light gradient boosting model. So we can go down here, select that from the menu, go in and select the predefined distribution of hyperparameters to consider. But this time we're actually going to mix it up. Instead of doing that random search to select the hyperparameters, we're going to use an evolutionary search-based optimization method with a higher search budget, but a more noisy evaluation method. So instead of using a 5K fold, we're just going to do 3 repeated split halves, again, though stratifying by sex. In general, the idea here is that we've defined 3 reasonable machine learning pipelines. Now that we have those models defined, what we can do is go into this evaluate menu, select our target variable, choose one of those pipelines to evaluate. We can select multiple metrics. This scope would let us, if we wanted to try with just one set of features, we'll just use all of them. Then we can go in, give the job a name, define how many cores we want that job to run on. We can just use all of them available on my computer. And then we're going to do a 5-fold cross-validation stratifying by sex on that full training set that we defined earlier. So now we can hop into the results page, and this is where you can monitor submitted jobs. And given the length of this presentation, I'll spare you from just sitting here and watching the progress bars move forward, and I'll just skip ahead in the video to where we've submitted all 3 of those pipelines with those same evaluation parameters. Here we are. We can go in, open all 3 of the jobs, look at some summary statistics as computed by them, and just quickly eyeballing this, we can see that the light gradient boosting model is working the best. So let's hop in and run the light gradient boosting model on the test set. So before, all of those were just on the training set. So now we're evaluating it explicitly on the test set. From here, next steps might include calculating feature importances, estimating the role of covariates, or trying different subsets of features, to name a few. Although support for some of these features within this GUI version of the application are still being developed, the base library written in Python is available for those who are comfortable with programming and want more flexibility. Finishing our example, we can note briefly that performance on the test set matches closely to our estimated generalization on the training set. To wrap it up, machine learning-based analyses can complement the traditional set of statistical tools in a number of ways, and I hope that a tool like this can make it easier for researchers to jump in and give it a try. Importantly, this work wouldn't be possible without the help of a number of people. I also want to mention that if anyone is interested in getting involved in any way, from trying it out or to contributing, if you have any in-depth questions, please get in touch with me. And of course, thank you for watching.